In part 1 of our lesson on simple harmonic motion, you will learn about the position function used for simple harmonic motion. Simple harmonic motion is what we use to describe objects that oscillate. And the position functions will be in the form of either s of t equals a cosine of omega t, or s of t equals a sine of omega t. Now, omega is taking the place of letter B that we've been using in all of our graphing. We use omega because as you go on in your studies and head into engineering or physics, you will run into equations that use omega, and so we want to expose you to that now so that you get some experience with it. Because omega is acting like letter B, everything you've learned about the coefficient of the variable still applies. And also notice that the variable is t instead of x, because t will stand for time, because objects oscillate over time. So that's why the function notation is s of t versus being f of x. So the period will be 2 pi divided by omega, because remember, the omega is acting like b, and since these are cosines or sines, we know the normal period is 2 pi. Now we have a new concept called frequency, and frequency is just omega divided by 2 pi. So notice that frequency is just the reciprocal of period. Amplitude is the absolute value of A as it has always been. Now notice in these equations, because there's no C or D, there will be no phase shift and there will be no vertical shift. There's only going to be the amplitude, which will give us vertical stretch or compression, and the period is 2 pi over omega, which could be a horizontal stretch or a horizontal compression. When an object is at rest and not oscillating, we say that it is at equilibrium. So equilibrium is the zero position of the object. Let's get an idea of how this will work. Suppose we have a weight on a spring, and that weight begins at its maximum height and is then released. If we plot the height of the weight over time, you can see that it traces out a cosine wave. So when we have s of t is equal to a cosine omega t, we know its amplitude will be a, which means the smallest y value will be negative a, the biggest y value will be positive a. Its period is 2 pi over omega, so it will look like a cosine wave when it's been pushed up so that it starts at its maximum position. So it will look like this. Now suppose instead we had the weight on the spring and we pulled it down to its minimum position and then released it. Looking at its height over time, we see that that traces out a negative cosine wave. So when s of t is negative a cosine omega t, we know it's been pulled down to its minimum position. It will hit its max halfway through, come back down, and end up at its lowest position at the end of one cycle. If the weight on the spring begins at its equilibrium position and moves upward first, and we plot the oscillation over time, we see that that will trace out a positive sine wave. So S of t equals a sine omega t will start at equilibrium, go up to its max, come back to equilibrium, down to the min, and end at equilibrium. And finally, if the weight begins at equilibrium and moves downward first, we see that its oscillation will trace out a negative sine wave. So S of t equals negative a sine omega t will start at equilibrium, move down to the min, back to equilibrium, up to the max, and then end at the equilibrium position. So the position function for simple harmonic motion only comes in 4 flavors. It's either a positive cosine wave, a negative cosine wave, a positive sine, or a negative sine. Those are the only 4 types of models that we'll use for simple harmonic motion. And you'll always know which one to use because if it starts out at its max, you know you're going to be using the cosine wave. If it starts out at its min, you know you'll use the negative cosine wave. If it starts at equilibrium and moves upward first, you know you're using the sine wave. And if it starts at equilibrium and goes downward first, you know you're using negative sine. Suppose you have an astronaut in outer space going to run an experiment. They will feel no effects from gravity and no effects from air friction, and this is what happens in simple harmonic motion. Now suppose you have a person on planet Earth going to run the experiment where they experience gravity and experience air friction. This is what's called damped harmonic motion. So let's see what happens now. If we have a weight on a spring and each of them pushes the weight up and then releases it. You can see that on planet Earth, the weight will eventually stop moving because of the forces of gravity and air friction, where for the astronaut, the weight will move forever and ever and ever, and that's what we're going to be studying right now, simple harmonic motion. In this example, a weight hangs on a spring. It is pushed up to an initial position of 18 centimeters and then released. It takes 2.5 seconds to complete one oscillation. Now, because the weight begins at its maximum height and is then released, we know that its displacement over time is going to trace out a cosine wave. So now let's get this into your notes. We'll make a little coordinate plane here. We know that the weight is pushed up to an initial height of 18 centimeters. So we know this is as high as it's going to go. And then we know that it will bounce down, and the lowest it will go is negative 18. We've said it's going to be a cosine. And now we're told that the time for one complete oscillation is 2.5 seconds. Now, one oscillation is the same thing as saying one cycle or 1 revolution, or 1 period. So we know that the 1 cycle here ends at 2.5 seconds. And of course, the height is measured in centimeters. Now, because it's a cosine, we know that S of t is going to have to look like a cosine of omega t. And our job is to figure out a and omega. So we've got S of t equals, a is pretty easy to figure out. The amplitude here, it's easy to see, is 18 times the cosine. Now we do need to figure out omega. And we know that to figure out omega, we use the period. And we know the period is 2 pi over omega. And we have to set that equal to 2.5, or I think I would rather write this as a fraction. So if this is 2.5, I know that's the same as 5 halves. So we'll call it 5 halves over here in our equation. Now we'll cross multiply this 2 up times the 2 pi, so that becomes 4 pi. The omega will cross multiply up on the right hand side, and then the 5 can cross multiply down on the left hand side, and we see that omega is going to be 4 pi over 5. Then we know the argument of our cosine function is going to be 4 pi over 5 t. So now we've got our position function, and we can use it to answer the rest of the questions in this problem. In part B, we have to calculate and interpret S of 5/3. S of 5/3 is going to equal 18 times the cosine of 4 pi over 5 times 5/3. Because remember, the function is S of t, so what this means is that t is equal to 5/3 seconds. This is going to become 18 times the cosine of 4 pi over 3 once those 5's cancel. We know that the cosine of 4 pi over 3, if you think of it on the unit circle, and in quadrant 3, cosine has to be negative, so we get negative 1/2. 18 times negative 1/2 is negative 9, and the units of height are in centimeters. So this means the object is at a height of negative 9. Now when they're asking you to interpret what that means, they're asking you to write a sentence. And so we would say that the weight is 9 centimeters below equilibrium. And that's what they're asking you to do when they're asking you to interpret. What they want you to show is that you understand that if the position is negative 9, that means that the weight is 9 centimeters below the equilibrium point. In part C, they ask us to find the frequency of the oscillation. Frequency is defined to be omega over 2 pi. Remember, omega was 4 pi over 5, and we have to divide that by 2 pi. So this becomes 4 pi over 5 times 1 over 2 pi. Now the pi's will cancel out. 2 goes into 4 twice. So we're going to end up with 2/5. The units of frequency are going to be in cycles per second here. We can also find frequency because we know it is the reciprocal of the period. So this would become 1 divided by 2.5, which we know we can write as 5/2, which of course turns into 2 over 5. Now, to help you understand the units a little better, if we think about frequency as being the reciprocal of period, we know that period tells us the time per one cycle, so then it makes sense that frequency would be the number of cycles in a unit of time. If period is time per cycle, frequency is cycle per time. In this example, we're told that an object oscillates according to the following equation. S of t is equal to -12 times the sine of 3 pi t. S of t is going to be measured in centimeters. T is going to be measured in minutes. It's CYU time, so pause the video, work the example on your own, then restart the video to check your answer. I think it will benefit you to draw a little picture of what's happening. It just helps you think a little easier. We know that we're going to have a negative sine wave. So that means it starts at the equilibrium position and goes down first, hits the min, comes back to equilibrium, then goes up, and then ends at the equilibrium. The amplitude is 12, so we know it's going to get as small as -12 and as big as 12. Now we can figure out the period because we know what omega is. To find the period, we're going to do 2 pi divided by omega. So that's going to be 2 pi divided by 3 pi. Be very careful. The pi is part of the omega. Remember that the argument of this function is omega times t. So whatever is multiplying the t is omega. So omega is 3 pi. The period works out to be 2/3, and we know that time is in minutes. So we can come up here to the graph and put 2/3 minutes, and we might as well label that the height is being measured in centimeters. So in part A, we have a really easy question. What is the maximum height the object reaches? We know the max is just going to be the amplitude, which is absolute value of -12, which is 12, and our units are centimeters. In part B, it asks us, when will it first reach its maximum height. So what this question is asking is, when does S of t equal that maximum height, which we just found to be 12? So we know the equation for S of t is negative 12 sine of 3 pi t, and we want to know when that is equal to 12. We're trying to solve for t, so first we'll divide by negative 12, and now we have that the sine of 3 pi t is equal to negative 1. Now let's think our way through this. We know that the sine of something has to equal negative 1. The sine of anything, I'll let A stand for anything, has to equal negative 1. Now think about a point rotating around the unit circle. When is the first time the value of the sine function is equal to negative 1? Well, that occurs when A, our argument, is equal to 3 pi over 2. That's the first time that that will happen. We can use this result to say that sine of 3 pi t will equal negative 1 when its argument equals 3 pi over 2. So we take the argument of this sine function, which is 3 pi t, and we set it equal to the angle that we know the sine will be negative 1, which is 3 pi over 2. We have to get t by itself, so we can divide by 3 pi. I think it's safer to multiply by the reciprocal. So we'll take 3 pi over 2 and multiply by 1 over 3 pi. We see the 3 pi's are going to cancel, and we are left with t is equal to 1/2. And we know that the units of time in this problem are minutes. Now there's a second approach we could have used to solve part B in finding the maximum height. We could have turned to the graph that we sketched earlier. We know that it starts at 0 and the cycle ends at 2/3 of a minute. So then easily we could find the midpoint because it would just be half of 2/3, which is 1/3. Then the quarter point would be half of 1/3, which is 1/6. So we've got 1/6, then this would be 2/6, which is 1/3. Then the 3/4 point would have to be 3/6, which is 1/2. So that's another way, using the graph, that we could see that the maximum would be attained when t is equal to 1/2 minute. In part C, we have to find the period and the frequency of the motion and make sure that we indicate the units. We know that period is defined to be 2 pi over omega, and in this problem we know that omega is 3 pi, so the period is 2/3, and we actually figured this out earlier. We know the units are minutes. Now the frequency We could do omega over 2 pi. We get 3 pi over 2 pi is equal to 3/2. And remember the units now. Think your way through. We know the period means it's a minute for a cycle. So the frequency then is how many cycles per minute. Some of you may have chosen to find the frequency by doing 1 over the period, and that's fine. So you would have said 1 over 2/3, which gets you to that same answer of 3/2, and it would be cycles per minute. Either way of calculating the frequency is fine. In part D, we have to calculate and interpret S of 5 over 18. Just a quick reminder that that means T is equal to 5 over 18 minutes. So we're solving for S of 5 over 18. That's going to be negative 12 times the sine of the quantity, 3 pi times 5 over 18, which is equal to negative 12 times the sine. Well, 3 goes into 18 6 times. So the argument of the function becomes 5 pi over 6. We get negative 12. And from our unit circle, we know that the sine of 5 pi over 6 is 1/2. So negative 12 times 1/2 becomes negative 6. And the units in this problem for S are centimeters. Now to interpret S, we know that that negative sign there means that the object is going to be below equilibrium. So we would say the object is 6 centimeters below equilibrium.